To multiply 23 by 17, Russian peasants used a method that needs no times tables.
No times tables at all, then how do you multiply anything?
Watch, write the two numbers side by side. Then repeatedly halve the left column, dropping any remainder, and double the right. 23 halves to 11 to 5 to 2 to 1. At each step the right column doubles. 17, 34, 68, 136, 272.
Wait, we just cross out the even rows.
We keep only the rows where the left number is odd. 23, 11, 5, and 1 are odd, so they stay. 2 is even, so its row is struck out. Add the surviving right column. 17 plus 34 plus 68 plus 272 is 391. And 23 times 17 is 391.
But why does halving and doubling land on the right product?
Because halving the left number tracks its binary digits, and doubling the right keeps the matching place values. The whole algorithm is repeated doubling with a conditional add. No multiplication table anywhere. The same shape computes powers. To raise a number to a power, we do not multiply one factor at a time. We square. Computing a raised to the 8th the obvious way takes 7 multiplications. A times A times A, 8 copies in a row.
Hold on, how can squaring beat that?
Because a raised to the 8th is a squared, then squared again. Square it to get a squared. Square that to get a raised to the 4th. Square once more for a raised to the 8th. 3 multiplications instead of 7.
And we are always allowed to regroup the product like that.
That is exactly the one law we lean on, associativity. A times B, then times C equals A times the product of B and C. We may regroup a product without changing it. That freedom is the entire source of the speedup. It is not a trick. Given associativity, repeated squaring is inevitable. And the gap widens fast. Computing A raised to the 1000 the naive way is 1,000 multiplications. By squaring, it is about 10.
1,000 down to 10. So if it is not really about integers, what does the algorithm actually need?
Strip the integers away, and that is the whole question. 2 things, an associative operation, and an identity element. A value that does nothing when you combine with it. That structure has a name. It is a monoid. And monoids are everywhere. Integers under multiplication with identity 1. Square matrices under multiplication with the identity matrix. Strings under concatenation with the empty string. Functions under composition with the identity function. Rotations and permutations too.
Don't we also need A times B to equal B times A?
Notice that we never asked for that. Commutativity is exactly what we did not require. That omission is deliberate. Matrix and quaternion multiplication are not commutative, but the algorithm never swaps operands. It only regroups them. Demanding commutativity would have thrown those examples away. So the same power code runs on any monoid. The only question left is what x raised to the n means once x is no longer a number. Here is the call, and we are going to fix it in place. Power of x to the n. We will not touch the code, we only change what x is. When x is an integer, power gives ordinary exponentiation. 2 raised to the 10th is 1024. Nothing surprising yet.
But what if x is not a number at all?
Then watch. Let x be the 2 by 2 matrix, 1 1 on top and 1 0 beneath. Its powers carry the Fibonacci recurrence. Raise it to the n, and the top right entry is the nth Fibonacci number. The same squaring that computed a raised to the 8th now computes Fibonacci of 1,000,000 in about 20 matrix multiplications. We changed the structure, not the algorithm. Fibonacci was hiding inside matrix exponentiation all along.
Same code, and now it is Fibonacci.
Let x be a unit quaternion, a rotation in 3 dimensions. Multiplying quaternions composes rotations. So power of x to the n is the rotation applied n times. Turn by a fixed angle n times over in a logarithmic number of steps.
Is there anything this does not work on?
Try the strangest one. Take the tropical semiring, where addition becomes minimum and multiplication becomes plus. Build the adjacency matrix of a weighted graph. In this semiring, matrix multiplication adds path lengths and keeps the smallest. So the nth power of the matrix holds the shortest paths that use n hops. The same power code is now a shortest path algorithm.
The exact same code finds shortest paths.
One algorithm. Integers, Fibonacci, rotations, shortest paths. The code never changed, only the algebra underneath it did. This is Stepanov's central idea. Algorithms arise from algebraic structure. The Peasant algorithm is not really about integers, it is about monoids. Once you see that, you start to find it everywhere.
So the algorithm was never really about numbers. So what does power actually require of a type?
An associative operation and an identity. A monoid and nothing more. State that requirement precisely, and the algorithm runs on anything that satisfies it. In modern C++, you can write that requirement down as a concept, the exact interface power needs. Any type that provides it, integers, matrices, quaternions, tropical numbers, simply works with no special cases.
So where do you actually start?
The lesson runs backward from how we usually code. Do not start with the algorithm. Start with the structure. See the structure first, and the algorithm follows.